function and their steady state errors. Okay, so let's start with the topic. So what is a type of a system? As we know that the open loop transfer function of a system, it is given by the equation GS equals to K So this is how we represent the open loop transfer function of a system. Now in this expression, if the value of this, the power of this n, it denotes the type of a system. Whatever will be the value of this n, that will be the type of the system. Suppose n is equals to 0, so that system is called type 0 system. If the value is of n is 1, then that system is called type 1 system. Similarly, type 2 system, type 3 system, and we have n type of systems. So this n, it determines the type of a system. Now for these type of the systems, these various systems, we will calculate the steady state error. Okay, so let's start with the first type 0 system. Also in this open loop transfer function, this K, it represents the forward path gain of the system, and n is the type of the system. So let us start with the type 0 system. So for type 0 system, the value of n is equals to 0. So in this equation which we have written, that this is the open loop transfer function, put n equals to 0 here. So for type 0 system, the open loop transfer function GSHS will be given by K we have put here s to the power 0, so it will become 1. So here we have the transfer function, open loop transfer function for type 0 system. Now we will see that what will be the value of the steady state error for unit step input, for unit ramp input, and for unit parabolic input. Okay, so what will be the effect on the steady state error depending upon the type of the system. So first we will have for step input. So for step input, we were having the steady state error, or we were having the static error coefficient as the KV, that is the static position error coefficient. So KP, that is the position error coefficient, its value is given by limit s tends to 0 GSHS. Okay, so Kp is equals to this. This is the static position error coefficient. Now putting the value of GSHS into this equation, and let's calculate that what will be the value of this static error coefficient. So Kp will be equal to limit S tends to 0 and GSHS is K1 plus STA. Okay. Now apply the limits. S tends to 0. So this will become 0. This term will be 0. This is also 0 and this is also 0. So we are left with only 1 in these terms. So the value of Kp will be equals to K. All other terms will become 1. So we are left with K only. So Kp will be equals to 1 for step input. Okay. Now we have the steady state error. So steady state error, that is ESS, it is given by 1 upon 1 plus Kp. So 1 plus limit S tends to 0 GSHS, or we can say that it is 1 upon 1 plus Kp, and here Kp is equals to K, so it will be 1 upon 1 plus K. So for step input and type 0 system, the steady state error is equals to 1 upon 1 plus K. Okay. Now taking the next input, that is the ramp input. So for ramp input, we have the static velocity error coefficient, and static velocity error coefficient is represented by Kv. Okay, so Kv, its value is equals to limit S tends to 0 S GSHS. Putting the value of GSHS in this expression, we will get Kv equals to limit S tends to 0 S GSHS was K So we have multiplied this S with the GSHS. Now apply the limits. When we apply the limits, we will put S equals to 0. So this whole term will be equal to 0. So Kv will become 0. So for ramp input and type 0 system, the static velocity error coefficient is equals to 0. Now let us calculate the steady state error. For this, we will have putting the values. This was equals to 1 upon Kv, and Kv is equals to 0. So 1 upon 0. So ESS will be equals to infinity. So for type 0 system and for the ramp input, the steady state error, it is equals to infinity. Now the third input is the parabolic input. So for parabolic input, we are having the static acceleration coefficient, that is Ka. So Ka, it is equal to limit s tends to 0 s square gs hs. Okay, put the value of gs hs here. We will have static error as okay. We have substituted the value of GSHS here for type 0 system. So apply the limits, s tends to 0. So this whole expression, it will become 0. So Ka will be equal to 0 for type 0 system and for parabolic input. Now calculate the steady state error again. So steady state error, will be ESS equals to okay, and this is 1 upon Ka. Here Ka is 0, so it will be equals to infinity. Okay, so for parabolic input also the steady state error is infinity. So we have calculated the steady state error for type 0 system when we have step input, ramp input and parabolic input. Now take the case of type 1 system and again calculate the steady state error for these three inputs. So starting with the type 1 system, so what is a type 1 system? In the type 1 system, we will have the value of n, that is the power of s in the denominator, the multiplicity of the poles, that n is equals to 1. Okay, so this open loop transfer function GSHS, which we have studied in the first, that what is GSHS? It is K 1 plus STA 1 plus STB and onwards, and this we have 1 plus ST1 1 plus ST2. Here we were having s to the power n, so n is equals to 1, so we will have s here. For type 0 system, n was equals to 0, so the s term, s to the power 0, it is 1. Okay, so we have this open loop transfer function for type 1 system. Now let's take the case when we have first the step input. So for step input, we have again the position, static position error coefficient Kp, and Kp is given by limit s tends to 0 GSHS. Put the value of GSHS into this, so Kp will be equal to okay. So when we put this s equals to 0 here, then we will get the value of kp as infinity, because 1 upon 0, or we can say k upon 0, it will become infinity. So kp will be equals to infinity for type 1 system. Okay. Now calculate the steady state error. So steady state error is ESS equals to 1 upon 1 plus limit, or we can say that it is equals to 1 upon 1 plus kp, and kp we are having here as 1 plus infinity, so it will be 1 by infinity, or we can say it is equals to 0. Okay, so steady state error for type 1 system and step input, it is 0. Now calculate for ramp input. So for ramp input, we are having the static velocity error coefficient as limits s tends to 0, s, gs, hs. Putting the value of gs, hs in this expression, we will get s, and gs, hs is k. This s and s, they will be cancelled, and we are left with this term. Applying the limits, s tends to 0, so this will become 1, 1, 1 and 1. So we are left with k. So kv is equals to k. So for ramp input and type 1 system, we have kv equals to k. Let's calculate the steady state error. So steady state error, it is given by ESS, that is, it is 1 upon kv, and kv is here equals to k. So steady state error will be equals to 1 upon k for type 1 and ramp input. Now taking the third case, that is for the parabolic input. So for parabolic input, we are having the acceleration, static acceleration error coefficient as limit s square gs hs. Putting the value of gs hs, we have so for parabolic input, we have the acceleration, we have put the value here. So applying the limits, we have the acceleration coefficient Ka equals to this limit. When we put s, this s will be cancelled to this, and when we put 0 here, so this whole term will become 0 and Ka will be equals to 0. So for type 1 system and for parabolic input, we have the constant Ka as 0. Now the steady state error for this, steady state error, that is ESS, it is equal to, for the parabolic input, it is 1 upon limit s tends to 0. We have s squared gs hs. Or we can say that it is equal to 1 upon Ka. So here Ka is 0, so 1 upon 0, that is, it is infinity. So steady state error for parabolic input and type 1 system, it is infinity. Okay. Now let us study for the type 2 system. Okay. So for type 2 system, we have, what will be the open loop transfer function for it? So for type 2 system, we have n equals to 2. So its open loop transfer function, that is GSHS, it will be K here we will have s to the power 2 because it is a type 2 system. And here we will have 1 upon st1, 1 plus st2. Similarly here. Now applying the various inputs. So first we have for step input. So for step input, we have the position error coefficient Kp as limits s tends to 0 GSHS. Putting the value of GSHS here and applying the limits, we have value of GS as so when we apply the limits s tends to 0, then this will become 1. This is 1. This st is 0 and 1 plus 0, it will become 1. Here also 1 plus 0, 1 plus 0, 1 plus 0. So we will have k upon s square. Now putting s equals to 0 here in s, so we will get k upon 0. So it will be equals to infinity. Okay, that is k by 0 is infinity. So kp will be equals to infinity for type 2 system and step input. Okay, now calculating the steady state error, we have steady state error as that is ESS, it is equals to 1 upon 1 plus limit s tends to 0 GSHS. That means it is equals to 1 upon 1 plus Kp. Now Kp, it is infinity, so 1 upon 1 plus infinity, it will be 1 upon infinity. That means it is ESS equals to 0. So steady state error for type 2 system step input, it is 0. Okay. Now for ramp input. So for ramp input, we have the velocity error coefficient. So velocity error coefficient is given by, so for ramp input, we have Kv equals to limit s tends to 0 and s GSHS. So putting the value of GSHS, we will get Kv equals to limit s tends to 0 s and GSHS is k because it is a type 2 system, so we will have s square. So this s will be cancelled with this, so we are left with 1 by s here. So putting s equal limit as s tends to 0, so we will have this all as 1 and we are left with k by 0. So k by s and s is 0, so k by 0, that means it is infinity. So kv for type 2 system, it is equals to infinity. Now calculating the steady state error. So steady state error will be steady state error is given by ESS 1 upon limit S tends to 0 S GS HS. That means it is 1 by kV, and kV is what? Infinity, so it will be equals to 0. So steady state error for ramp input type 2 system, it is 0. Now calculating for parabolic input. So for parabolic input we have the acceleration coefficient, that is Ka, and Ka it is given by limits S tends to 0 S square GS HS. Again putting the value of GS HS, we have Ka equals to limit S tends to 0 S square K 1 plus STA 1 plus STB So S square and S square, they will be cancelled out, and here we have S equals to 0 if we put the limits. So it will be 1, 1, 1 and 1. So it will be equals to K. So for parabolic input type 2 system, we have the acceleration coefficient as K. Now calculating the steady state error. So steady state error will be, that is ESS equals to limits S tends to 0 S square GS HS. Okay, that means it is equals to 1 upon this, so it will be 1 upon Ka, and Ka is what? K here. So steady state error will be equals to 1 by K for the parabolic input and type 2 system. So we have calculated the steady state error for all the three types of the system, that is type 0, type 1 and type 2, and also for the three input, step input, ramp input and parabolic input. Let's summarize what we have studied. Here we have the type of the system. Here we have the error constants or error coefficients, and here we are having the steady state error. We will calculate the steady state error for the three inputs. First we have step, then ramp and then parabolic. So for type 0 system, our error constants, that is Kp, Kv and Ka. Okay, so we have this for type 0 we have Kp as K0, 0. Steady state error will be 1 upon 1 plus Kp, 1 by Kv and 1 by Ka. Okay, these are the values. So we are given this. So if we, for type 0 system, it will be 1 upon Kp, and this 1 by Kv, it is equals to infinity, and 1 by Ka will be equals to infinity for type 0. For type 1, we have infinity K 0, and this will be 0, 1 by K and infinity. For type 2, we got position error coefficient, these as infinity, this is K 0, 0 and 1 by K. Okay, so this is what we have studied in this video. That is, for type 0 we have Kp as K and Kv Ka as 0. For type 1 we have Kp infinity, Kv as K, Ka as 0. This is increasing. This is you see that K we have got for 0, type 0, type 1 and type 2. Here also we have followed a pattern. Okay, so it will be easy for you to learn or remember this table. I hope this video is clear to you. Thank you.